Okay, good afternoon. So let's start the class. So today we will look at a special topic called Stirling's Formula or Stirling's Approximation. So this is a formula that approximates what? Approximates the value of this n factorial. So we'll see this. So this is not a particular result that is related to the counting problem, but the approximation is useful because in all the combinatorial terms, we have like Cn choose n choose k or the Pnk, you will see a lot of n factorial. So it is useful to know approximately what is the value of this n factorial so that we can estimate the term n choose k. So after we talked about this Stirling's formula, we will move on to a new topic, the generating function. Okay, so here, okay, so how does the approximation looks like? Okay, so it is like n factorial is approximately equal to what? It is approximately equal to this term, square root of 2n pi, or 2 pi n, perhaps, multiply with n divided by e to the power n. Okay, so this e is the base of the natural log. So, but in some sense, this is not a very accurate writing. It is because as n tends to infinity, the difference between this term and this term will tend to infinity. You understand my point? So for instance, let me quote some figure for you. Let me use the blue pen. So okay, so let's take a look of 1 factorial. Okay, the value of 1 factorial, if we compute the exact value of this one, 1 factorial is what? 1. Okay, good. And then using this Stirling formula, so by Stirling, then we will get 0.9221. So this, we can use a calculator to calculate this. And then if we look at 2 factorial, so the value of 2 factorial, this is okay, this is equal to 2, right? And the value of this one is 1.919. Okay. If we look at 5 factorial, the exact value of this one is going to be 120, we notice. And then the value here is 118.019. Is that okay? And let's take a larger number this time. Let's look at 100 factorial. So this is going to be a large number. And roughly, it is 9.33 times 10 to the power 157. So a large number. But if we use Stirling's approximation, we get what? We get 9.32 times 10 to the power 157. Is that okay? So if you look at this, the difference between them is actually getting larger and larger. So the difference between this is like 0.08. The difference between this one and this one is already 0.1. The difference between this, or 0.08 again. But the difference from this one to this one is close to 2. So if you look at the absolute difference between the exact value and the Stirling value, it is getting larger and larger. And this one is a huge number. This is 9.33 times this one. This is 9.32 times this one. So the difference will be what? The difference will be 0.01 times 10 to the power 157, a super large number. Is that okay? But on the other hand, the difference in ratio is getting closer and closer. Okay, so in the sense, we are going to see that rather than writing this approximate value, this is what we hope to get. We hope to get as n tends to infinity, the ratio between them, n factorial and this approximate value, square root of 2 pi n times n over e to the power n is going to be equal to 1. Okay, so this is by means of approximation. Is that okay? The absolute difference could be huge, but the ratio is going to be smaller and smaller and smaller and getting close to 1. The difference in ratio is going to be smaller and smaller and smaller. Okay? So this is what we are going to look at. And to prove this, any questions so far? Okay, to prove this, we just need to use some fundamental integration. Okay? So let's look at this curve. Okay, let me draw this curve. So here, idea is let's approximate what? Approximate the value of log, this is base e, of n factorial. Okay, so we want to approximate the value of log of n factorial. So if we find out the approximation value of this one, then we can find out the approximate value of n factorial. Is that okay? So this is the idea. Okay, and then let's look at this curve. Okay, let me try this. Let's look at the curve. Let's look at the curve. Y is equal to log x. So let's okay, so how does the curve look like? So this is 0, right? Right? So how does the curve look like? Like what? Like this. How does it look like? So it must be increasing, right? The larger the value of x, the larger, right? Log 1 is equal to 0, so it hit this point, 1, right? And then what? And then what is the slope of this curve? So what is the slope? So what is the value? What is the slope of this curve? What is it? So what is dy over dx? 1 over x, right? Okay. So the slope of the curve is 1 over x. So that means what? That means as x is becoming larger and larger and larger, the slope is becoming closer and closer and closer to 0. It's going to be flattened soon. Okay, so it looks something like this. Is that okay? Okay. So 1, 2, 3. Let's look at up to n. Okay. Okay. So we will look at this curve in two different ways. We want to bound. We want to find out what is the area between this one. So what is the area under the curve? So we want to So what is the area under the curve? So the area under the curve is easy, okay? So let me write down. So this area, so the area under the curve is equal to what? It's equal to integration of log x dx. Is that okay? And then we integrate it from 1 up to n. Is that okay? Okay. Anyone still remember how to do integration of this log x dx? So we can do integration by part. Okay. So trust me, yeah. After integration by part, we get something like this. We get this is going to be x log x minus x. Let's double check. Okay. Let's try to see if we differentiate this one, we get this one. Okay. So if we differentiate this one, we will get what? X times 1 over x plus log x times 1. So it is going to be 1 plus log x. And then if we differentiate this, it is 1 minus 1. Okay, so you get 1 plus log x minus 1. So cancel out, you get log x. Is that okay? And then this is starting from 1 up to n. And then this is equal to 1. So it's going to be n. So let me use this log n to represent base e. So we get n log n minus n. And then this is 0 plus 1 as the area. Let me double check. I didn't write down the area and the curve is equal to this one. So it should be equal to this. Okay. Okay. So we have this one. This is the area under the curve. So this is the first term. Now, we do a second thing. So what should we do next? Okay. We are still looking at this area, but this time we are going to give a lower bound on the area of this one. Okay. So let's do another figure. This is still y is equal to log of x. And this is y, this is x, this is 0, this is 1. So you get something like this. And then this is 2, this is 3, this is 4, this is n. Okay. Okay. Okay, so the next thing that we do is like this. We go to 2, we find out the intersection point here. So this is the value of log 2. Is that okay? And then we go to 3, we come up here. This is the value of log 3. Is that okay? And then we have, this is the value of log 4. This is n minus 1. So this is the value of log of n minus 1. Is that okay? And now we are going to, this time let's use another color. Do I have another color? Let's use the blue color this time. So we are looking at this one. Join these points. We join these points. Okay. So by observation, just by observation, so we need to prove it better that if we join this, we get this is a triangle. And then this is a trapezium. Is that okay? And then for this one, this is another trapezium. And so on and so forth. So we get the blue area. Okay? And then this time, we argue that, we claim that this red curve is always above this blue line segments. Okay, the reason why this is true, it is because this is a convex function, or you call it concave function, so that this curve is going to be above any, okay, so this is a convex function or concave function. It has a property that if you pick any 2 points in this curve, you join them, this line is always below the corresponding curve. Okay? So to check whether a curve is convex or concave is easy. Just differentiate it 2 times and then check whether it is always negative. Okay? If it is always negative, then it has this behavior. On the other hand, if it is always positive like this, then if you join any two points, then this line is always above the curve. Okay? Okay, so assume that the blue part is always below the curve, then what do we have? We will have what? The black area is always greater than or equal to the blue area. So the blue area is like this. Okay. And what is the area of this blue part? This is going to be equal to what? How do we calculate the area of this one? What is it? This area is not that difficult. So what is the area of this triangle? What is the area of the triangle? So this is, let's say this is the base and this is the height, right? So what is it? It's going to be log 2 over 2, am I correct? Because it is, the height is log 2, the base is log 2, the height is 1. So it is log 2 over 2, right? Okay, good. So the triangle is just, let me use ln. Log 2 over 2. How about the next one? How about this one? How about this one? What is the area of this one? You have the top part plus the bottom part. You add up these two, multiply with the height, and divide it by 2, right? So what is it? So it's going to be log 2 plus log 3. This number multiplied with 1 and then divided by 2. So it is just log 2 plus log 3 divided by 2. Is that okay? Good. And then the next one, we can write it. So it is going to be log 3 plus log 4 divided by 2. And then there are many more terms. Up to when? Up to the last term. What is the last term? The last term is going to be log of n minus 1 plus log of n, and then divided by 2. Okay, so we have this one. Okay, is that okay? Oh, this is nice. Okay, so how nice it is. Okay, so first of all, let me just write down log 1. Log 1 is equal to 0. I can always write it down. Okay, plus, how many log 2's do we have? 1. Okay, so we have a log 2. How many log 3? 1. Log 4, 1. So we can write down something like this. Plus, dot, dot, dot. Plus log of n minus 1. Am I correct? But there is a last term. This is just log n over 2. So we can simply write it as log n and then minus log n over 2. Is that okay? So far so good, right? Is that okay? So I add everything. I try to add everything up to log n, but I'm adding too much because we just only have log n over 2. So I need to minus log n over 2 to make it balance. Okay? What is the first part? What is log 1 plus log 2 plus log 3 up to log n? What is this? Without the minus, what is it? Log of, very good, log of n factorial. This is the reason why we can connect n factorial with this one. So we have log of n factorial. Is that okay? Minus log of n divided by 2. So this is the blue area. So far, if you take a look, this side is just a function of n. That side, you have log of n factorial is equal to something. So immediately, we can actually have a bound about this log of n factorial already. Is that okay? Okay. So, but let's do something more. Okay, so we hope to get the limit. We hope to show that the limit tends to a certain value. So rather than just finding a bound, so this is going to give us an upper bound of what is log of n factorial. Okay? And we also want to get a certain lower bound of log of n factorial. So that in that sense, we hope to get a tight bound of what is log of n factorial. So this is our target. Okay, so let's see. So you can guess already. So this time, we do yet another thing. So the blue part is doing what? The blue part is going to look at what is approximately the value, the area under the curve. Okay, we try to So we try to estimate the area by something that is below this curve. So to get the other side, we are going to estimate the area by something above the curve. Okay? So this is what we are going to do.